So today I'm going to start my ever lecture in the physics. I have here physics key, which is scholar publication, and physics book, and yeah, my notebook. And so let's get started. By the way, I'm studying in first year. Those you can see it by the 11th. There's not 11 here. So let's get started. So basically, yeah, this book is little bit messed up. Pardon me for that, because it's so. Yeah, here is the content page. Our first topic is measurements, as you can see. So basically we are going to start with the SLOs, which are these things. Which SLO means student learning outcomes. So at the end of the topic, it describes what a student will understand, what will student be able to explain it. So here is the, for example, this one: describe the scope of physics in science, technology, and society. State SI base unit, derived units, and supplementary units for various measurements. Express derived units as products and quotients of base unit. State conventions of indicating units on set. There's a set out in SI. So basically, these are the slows, which after this after after all this lesson we will be able to explain this thing. So let's best start with this is the starting paragraph saying that importance and scope of the science physics is not hidden from today's human being. Yeah, basically. So how we this books is not easy for a student to easily understand what he is studying. So I just made my own version of it. I don't know what if you can see it. So highlighting main important things. Yeah, my writing is not good as this book, but I will try to explain it. So starting with the measurements, let's open all these books and describe the measurements. So the physics chapter 1 in the key book, this is a concept map. Let me focus on it. Concept map. Here it shows the flow of the lectures, and here are the questions and their answers to it. You can study from here. It's a good place to study. Good book to study. But I'm gonna simply break it down, make it easy for everybody common student to learn fast and remember it quite easily. So basically, what is first you need, before starting a topic, you need to understand what you are going to study. You can study it by, you can get it, understand it by you looking at the SLOs, which are given in the book in the starting of the chapter, a unit. And you can also state that the topic is related to measurements because it's written there. So in this topic we will be able to learn different things about, for example, units, quantities, which are physical quantities which we can measure, and there are a lot of things: system, international, and supplementary units. It's not very hard, but let's get started. So basically in this measurement unit we cover about the mainly cover about the physical quantities. So I made a note here. Physical quantities. All measurements are used. All measurements are called physical quantities. Measurable quantities. All measurable quantities are called physical quantities. If you can measure anything, it will be called physical quantity, because if it physically exists, then and it is measurable quantity, then it will be called physical quantities, which are including which include mass, length, velocity, force, and etc. So physical quantities are divided in two categories, mm, two main categories. First one, first one is base quantities, and second is derived quantities. So what base quantities are? So base quantities are the fundamental quantities. For example, the minimum number of some books state these base quantities like this, that the minimum number of those quantities which are made by itself their own identity, or you can also explain it by the quantities in terms of which other quantities are defined. These are time, mass, length, current, temperature, and amount of substance, and light intensity. So these are the basic quantities which we use in our daily life to drive other quantities like force, velocity, speed, etc. So drive quantities are made using base quantities. There are 7 base quantities which are the time, mass, length, current, temperature, amount of substance, and light intensity. So you have got an idea of what drive quantities are this far, because the drive quantities are defined in terms of base quantities are called drive quantities, because these are derived from base quantities, which are these things: mass, time, and etc. So the base quantities are only 7, but drive quantities do not have any limit, because every day new new units are formed, new quantities are formed. So let's it was let's get back to next subtopic, sorry. International system of units. In 1990s, an international committee agreed on a set of definitions and standards to describe physical quantities. You know, these base quantities are those in based on this system of unit. So the system was called System International, SI. So SI stand for System International. These are called SI units. For example, Newton, seconds, kilogram, etc. So before 1960, different countries use different standards for example, I think some countries use pounds, some use kg for mass, and there are thousands of different standards internationally. So when somebody, for example, in science community, when somebody was measuring something, he measures the quantity in their own standards, and the rest of world did not understand what it is. So so they so in 1960s, what they did, all the science community people agreed on set of definitions, standards to for international understanding, for international exchange of information. So that's what SI unit or so next is supplement units. Now as we discussed before, that physical quantities are can be either base quantities or can be base quantities or derived quantities, but there are another quantities which do not fit in any of those. So these are called these are called supplementary units. The General Conference of Weight and Masses, which was this 1960s International Committee program. So the General Conference of Mass and Masses has not classified certain units of the SI units under either base units or derived units. These SI units are called supplementary units. These are plane angles and solid angles. So don't worry about this plane and solid angle. I will explain it later. First, let me explain the supplementary units. When International General Conference of Weight and Mass was held, it studied and about the base. It classified quantities into base and derived quantities, but there are some other units which belongs to measurement but were not classified as either base or derived quantities. So so then and another international committee was not held. So these angles, sorry, these units were called supplementary units. There are two types of units. One is plane angle and solid angle. This plane angle, which we can call it 2D angle, and the solid angle can also be called as 3D angle. These are the supplementary units are basically angles of geometry. So it cannot be it cannot be placed in base quantities or in derived quantities. So that's why they were classified as supplementary units. So as we studied, there are two types of supplementary units, plane and solid. So let's discuss what are radian and steradian. Basically, steradian is unit of plane angle. Remember, it's the unit of plane angle, radian. So a radian is a plane angle traced at the center of the circle by an arc of length equals to the radius of a circle. So let me grab my rough notebook so I can explain it by drawing by graphically, so you will understand it better. So here is my rough copy. I will try to explain it by graphically. It's not a circle, but just let's suppose this is the circle, and what radian is, it is angle traced by an arc. This is plane angle, which means it's 2-dimensional angle traced by an arc at the center of this circle. So which has two radii. Let's see, this is called, this is the angle, and this is called, this is an arc, radius, these two are equal, and it's the radian states that the angle is traced at the center of circle of length. The length of this arc is, remember, length of this arc, let's see, is equals to radius of circle. That's what the radian is, in which all these sides are equal. The length of arc is equal to the first radius, and you know the radius is same, and that's why it's equal. So the formula for the angle is theta is equals to 2 pi radian. So pardon me, my writing is very bad. Theta is equals to 2 pi radian. Rad is unit of radian, so don't get confused. and another is steradian. Remember, radian is 2D angle. We can write on paper. This is the radian. It's a 2D angle. But steradian is unit of solid angle, which means it's a three-dimensional angle. It's in definition. Let's see what I wrote in definition. It is a three-dimensional angle subtended center of sphere by an area of its surface equals to the square of radius of sphere. You might get confused in this place, so let me grab my book to show you diagram of this 3D. Yeah, here it is. So steradian is three-dimensional angle, which means it will be we can not discuss it on paper easily, but in third-dimensional simulation we can easily understand this. But let's suppose this is sphere and this is the angle. This is the area which subtend angle on the center, in which r square is area. Let's say this a is equals to square of this r. So remember, steradian is three-dimensional angle. This three-dimensional angle subtended at center of sphere by an area which is equals to the square of radius. It means there are two radius, multiply them and you will get the area of this area which caused the angle, which subtended the angle at center. So that's what steradian is. It's a three-dimensional angle, and the formula to calculate so let me write radian, and sorry, my writing is very bad. Steradian. Formula for steradian is theta is equals to area divided by r square, which also can be illustrated as a theta is equals to 4 pi steradian. This is what the formula is to find the steradian. And don't worry, in this chapter we are not gonna calculate something like that. So moving on to the next topic, scientific notations. Now, what are scientific notations and why would scientists make them? So what will you do to write, for example, this one point, sorry my pen is very 0.000025, or even much smaller than this, or let's say 56000. These are the quantities which take a long time to write. What if there were more zeros? You would not waste this and your time to writing this. So what a scientific notation is, this is a system in which numbers are written in the power of 10. For example, m multiplied by 10 to power p is called scientific notation. So if you write if you become scientist and you are writing these numbers, for example, this is the mass of an atom. I don't know what it could be, but let's suppose atom is very smaller, that it will be very less, it will be of very less mass. So you are not allowed to write this as the mass, because there are too many zeros, unnecessary zeros, and you have to avoid it by using scientific notations. So what do I mean by that? Let's say I'm gonna write this in standard form 0.00, sorry, I put points in there, 0.0025. How would I write this in scientific notation in the power of 10? So what we will do is move this point once, twice, and 3 times. Remember, you must always keep it to first non-zero digit. We cannot do this. This is a big example. We will write it as 2.5 multiplied by how many times we move it? Once, twice, and thrice. 10 multiplied by -3, because the number was lesser than 0, it will be counted as -3. This is scientific notation. What if I was going to write 67000? So this will be written as, for example, if there is no point, then it is at the last, remember. So we are moving this 0 point from 1, 2, 3, and 4. 6.7 multiplied by 10 raised to power 4, not the negative, because the number is greater than 0. So remember, this is the scientific notation. It's very simple, and let's read more about it so you can make a good understanding. Scientific notations are accepted internationally. It is internationally a practiced system. So there should be only one known digit, 0 digit left on the left of the decimal. So thus the number these are some examples. You already explained it here in my rough notebook, so you don't need to worry. So let's move on to it's not the third but another subtopic. It's called prefixes. Now what the heck are these? So prefixes are the letters or symbols written before unit of the measurement to represent certain specific power of the tens. Now we said that scientific notation are the numbers written in the power of 10, but prefixes are some symbols which are used before the unit, remember, unit of measurements, to represent certain specific power of tens. Some prefixes have power of 10 positive, which we call multiples, and some have negative powers of 10, which are called submultiples. So let me show you proper example of these prefixes. Let's go to book page number, I don't know where it is, page number 6. These table 1.5 prefixes, their symbol and their equivalents. So for example, let's 10 raised to power 1 will be deca, which symbol is Da, and deci, which is D, and it is in the negative. Deci is the smaller unit, remember, it will be in the negative, and the centi, which is HC. For example, let's for example 10 centimeter, 10 meter, 10 kilometer. These are the prefixes which represent certain number of certain power of 10. So here is the table. You can try to remember. If you can, then try to remember this thing, because some of these are very important. For example, let's say for example atto, hexa, deci, centi, micro, nano. These some are important for the MCQs purpose. uh, so you can try to memorize them if you want to, but I would recommend not to waste much of your time on this, because it will not take over, it is not most important topic in the physics is very bigger than this. So let me explain some of these. So centi is the centi is equivalent to 10 raised to power negative 2, and milli to negative 3, micro to negative 6. Remember, as you can see, milli is negative 3 and micro is negative 6. Some of the so powers are not given some certain names and symbols, so it will be easy, don't worry. Micro, remember, micro is very oftenly used. These micro, mini, centi, deci, deca, these are some commonly used units, sorry, prefixes. You might try to understand this. So nano, which is negative 9, pico negative 12, femto negative 15, and atto negative 18. So this was negative 15. So similarly, like in the positive ones, deca is the first one, which is for power 1 of 10. Kilo is power 1 power 3 of 10. Mega is 6th power of 10. Giga is 9th. Tera is 12th. Peta is 15, and exa, but I don't know how to pronounce it, but I will call it exa, and it's the power of 8, 18 power of 10. So this is not much important, but remember, try to understand these nano, micro, milli, centi, deci, kilo, mega, giga. These are some very oftenly used prefixes. And in the page number 6 of physics book, there are some prefixes. Try to look at these ones. Not much important, but you must look at it. So moving on to the next topic, we get is error and uncertainty. It's been 27 minutes. So how much of it is left, I don't know. Not much, I suppose, but let's try to conquer it. Errors and uncertainty. All physical measurements are uncertain and precise to some limit. So remember, in physics and science are the tools to measure. Physics is tool to measure the environment around us. Science is used to understand the environment around us, and we cannot understand it precisely. We cannot measure it 100% with 100% precision. So all physical measurements are uncertain and imprecise to some limit. Remember, none of the instrument has been built ever to calculate its 100% calculate with 100% efficiency. So remember this thing. There is the subtopic of this 1.4 1.4.1 error. What error is? Error is basically called mistake, but physics states that the difference between measured value and the acceptable value in any measurement is called error. Remember, difference between the acceptable measured value and acceptable value is called error. So what are the sources of error? Basically, sources of errors are negligence of or inexperience of person. If the person is not experienced, he will not be he will make it will he will make errors. It's very a greater chance of making errors. if the instrument is faulty, for example it's very old, for example 5 to 10 years old, then it will make some errors because it's not appropriate to use, it's faulty apparatus. And third one can be the method, inappropriate method and or technique which is used by the person. So these are the sources, these are the things which can cause errors. Just simple as that. And another next topic is uncertainty. So what is uncertainty? The estimate of the possible range of an error in any measurement is called uncertainty. Now you might be get confused, don't get confused, it's actually very simple. It's very simple. The estimate of possible range, remember, estimate of possible range of the error in many measurements is called uncertainty. It means we are not sure whether the calculation is true. So 100%, it can be 100% true, truth. So that's why we are giving it a range, possible range in which might which may have error. For example, we measure, if you are measuring length 10 centimeter plus minus, sorry, 10 plus minus 0.25 centimeter, this is the range of error. We don't know that this unit, sorry, the measurement is 10.25 centimeter or 9 point, what would it will be, I don't know, but just minus this from the 10 and you will get it. So basically it's the range between 10.25 and the, if you minus whatever this number is, 9 point, it will be 9.75. it is the range. We don't know whether what is the accurate measurement, but we know that it's between this range. So this is called range of error, which is uncertainty. It can be written like this one. So let us open a book to show, let me open a book to show you some of the uncertainty earlier. For example, this one, where it is this one, 22.5 plus minus 0.1 centimeter. So these are uncertainties. We don't know whether where does the measurement really lies, but we know that it has some specific range. So that is simply called uncertainty. It is the range of possible error. Remember, it's not an error, it's range of possible error. It gives the range in which a measurement, in which a real measurement, accurate measurement lies, but we don't know where it is. So that's why we write the uncertainty along with the measured value. So that gave us that it's not that this, for example, these are two values. We are saying that it's not this measurement, not neither this, but it can be between these two ranges, and that's what called uncertainty. It gives us the range which shows the possible error. It's not shows an error, possible range of error, and that's what called uncertainty. Now, what can be sources of uncertainty? How uncertainty comes? It's because limitations of instrument. We know that science is developed very much, but it's not developed that much to accurately measure anything. For example, length of this book, length of this pen, it cannot measure it 100% precisely because of limitations of instruments. These are what limitations of it. Uncertainty is caused by limitation of instrument. For example, the mass of radius of we cannot measure the radius of an atom, or electron. That these are some limitations of instrument we use to measure them. So, and other is natural variation in object under observation. For example, we are observing. Measurement is just an and observation and in nature different stuff happens, like climate change, temperature change, pressure change, atmosphere pressure, wind blowing, humidity, and all those variables which lies in the environment. And uncertainty can be caused by natural variables which affect the measurement. That's why some of these natural variables can affect the uncertainty and effects in sense of experimenter. It also caused by uh, untrained or inexperienced experimenter. So remember these in mind. These are very simple notes. And moving on to next subtopic, precision and accuracy. What is precision? Precision a precise measurement is the one which has less absolute uncertainty. For example, we say uh, we said that uncertainty exists in every measurement, almost every measurement. But precise value measurement is that in which the absolute uncertainty is lesser, which has more lesser the range of error. It will be more precise. It is associated with the least count of measuring instrument. Yeah, it is. For example, a meter rule cannot measure the length of this book accurately, but if we use some other instrument which calculate it to the further level, for example in points, in decimal points, the measurement will be different, because meter rule cannot give us a decimal points, the least decimal points. So it is also associated with the least count of measuring instrument. For example, we say that 1 year caliper, I don't know what is the exact least count. Let's see, 1 millimeter. So this is the range of possible error. This is the uncertainty. It means in the mere value, which is 10 meter, let's say 10 millimeter, give or take 0.1. This is uncertainty, and it has direct connection with precision. Precision is directly linked with least count. More or less the least count, more precise it measurement will be. So that's the idea of precision. Smaller the least count at the instrument, measure will be more precise, and vice versa. That's what I told you. It is determined by instrument being used. Yes, precision is also determined by the measurement instrument which is used to measure the quantity. So that's precision. So what is accuracy, by the way? Accuracy of measurement is the difference between your measurement and the acceptable correct answer. The bigger is difference, lesser the accurate your measurement. So that's what it is. It is the difference between your measured and the acceptable answer. And if the difference will be lesser, the accurate your answer will be more accurate. If the difference is higher, more difference can cause a less accurate measurement. So remember that an accurate measurement is one which has less fractional or percentage error. For example, percentage uncertainty. accuracy of measurement depends on the fractional or relative error, uncertainty in measurement. What basically this statement says that accurate measurement is the one in which it has less error in it. For example, if difference between the acceptable and a mere value is very less, which means it's, and when this uncertainty is very less, more accurate it will be. So that's what accuracy is. Smaller the fraction or percentage uncertainty, more measurement will be accurate, and vice versa. Accuracy means how closer a mere value is to the actual value. Remember, we cannot get 100% closer to any of measurements, but it is accuracy means how much closer we are to the actual value, how much our mere value is closer to the actual, which is the true value. That's what accuracy is. If you So there are some formulas to calculate absolute uncertainty, fractional uncertainty, pardon me, percentage uncertainty. So least count of measuring instrument, this is the formula. This is the absolute uncertainty in least. You, for example, I told you to write 10 plus minus 0.1 millimeter. This is the least count. Let's say this is the least count instrument, and this is the uncertainty. This is the absolute uncertainty. You can get it by just look at the least count of measuring instrument. It will be given on the instructions. Fractional uncertainty of absolute uncertainty measurement. Absolute uncertainty, which is this one, divided by measurement, will give you a fractional uncertainty or relative uncertainty. And last one is percentage uncertainty. Fractional uncertainty, which is this one, divided by 100%, will be percentage uncertainty, and absolute uncertainty divided by measurement to multiply by. Basically, percentage uncertainty is absolute, which is least count uncertainty, divided by measurement. Measurement is this one, 10. This one is the measurement. And for example, let's say 0.1 millimeter, so 0.1 divided by 10 multiply by 100, sorry, 0.1 divided by 10 is fractional uncertainty. And if we multiply that result with 100, it will be the percentage uncertainty. Let me grab my calculator to calculate this one, because I want to make you understand the whole stuff. So here is my calculator. I don't know whether you can see it or not. Let's say 0.1 divided by 10 is 1 to 100 is fractional uncertainty. This, and the percentage uncertainty will be, if we multiply the answer with 100, it will be 1%. The percentage uncertainty in a measurement like this one is only 1%. There is 1% uncertainty in the measurement. So I hope you have understand. If you didn't understand it clearly, there are some examples to indicate. There's an article, a big article, which I've just simplified it in my version, and there are some examples in the book from page 12 to page 15. You can read those articles if you want to, but I think my version is little bit good, but because I've just highlighted what is required. For example, in a select uncertainty is the least count of the measuring instrument. If you divide the least count of measuring instrument by the measured value, it will give you fractional uncertainty, and if you multiply that fractional uncertainty with 100, you will get percentage uncertainty. So I've also given an example from the book. I suppose I don't know whether it's from book or just I've written it myself, but let's